Okay, so we are in our third lecture. So before I move on, if you have any doubt, any question from yesterday's lecture. Okay, all right.
Can you hear me?
Yes, I can hear you. Yes.
So I had a small.
You introduced the concept of the weight. So I was thinking if what if we treat the weights as the parameter just like theta1, theta2, theta3. So can that work as well?
Can you repeat your question? Because I could not hear the first part very clearly. Could you please repeat it?
So my doubt is, can we treat the weights W1, W2, W3 just as the parameters theta1, theta2, theta3, which are unknown? So will that work?
Oh, I see. So you mean for the locally weighted regression, right? For that part you're talking about.
Yes.
Okay. So of course you can learn these weights, but then you have to learn using some information. Okay. So that weight has to be a function of some information. So in this case, the information could be, of course, the distance, but yes, in principle, you can learn that. So what we have here is the distance. That's the main information that we are using here. And the function that we used is a basically Gaussian function that we are using. So instead of that, you can actually learn a particular function where the input to this function would be distance of the weight, distance of between 2 points. And then yes, you can basically learn these parameters as well. Okay. So makes sense? Yeah, okay. Any other question?
So I had a doubt in the weight function.
Okay.
So there we calculated in the weight function we were calculating xi minus x test.
Right.
And my question here is, so is there a specific order as to which element we need to use for xi and x test? Like can x test be any test set and any test set with a random arrangement of elements, or we need to?
So X test is a single sample test sample for which you are trying to predict the level, output level. So X test here is the single sample, not a set.
So x test here is not an array like which has multiple features. It's just a
So
single.
yeah, this is a test sample with it can have multiple attributes. So typically n dimensional feature vector, but it's a single sample. So basically you can consider this as a single row or like single array, something like that, people think in terms of implementation. So then what you do, you basically xi is the ith training sample and x test is the test sample, and you compute the Euclidean distance between these two.
Okay, sir. Okay, sir. It's clear
Okay.
now.
Yeah. Any other question? All right. So thank you for joining.
Sir,
Yeah, please.
so there that test case will be same for all the I for all i's, right? For all x's.
So in theory it is, yes. So because we are using the distance weighting, distance based weighting measure here. So that's in principle you can basically we can consider all the examples that is available in your training set. But there is a catch. The catch is that of course that is going to be computationally very complex. Okay. So you can actually reduce that set because you do not need all the points. So you can basically reduce the set by using some kind of approximate KNN never search. So you basically first you pre-process the training set to find out several regions, some kind of clustering technique, and then when a test sample comes in, you only simply compare the test sample against the centroid of some cluster and then pick those points in that clusters as your the exercise, and then you do it. So these are of course the approximate approaches that you can apply just to reduce the burden, the computational complexity. Okay. So, but in the slide which I mentioned, it's essentially all the training samples that we are taking. Make sense?
Okay, sir.
Okay. Any other question? All right. So let us get started. So just a quick recap of what we had done yesterday. So we started talking about supervised learning. So there is, could you mute, please? Okay, thank you. So we started talking about supervised learning. This is one of the most widely used learning techniques in practice. And we talked about regression, which is one type of supervised learning. We looked into linear and non-linear regression and also saw how we can estimate the parameters. We talked about locally weighted regression, so which essentially uses the closest neighbors to build the regression model. So that's the kind of things that we looked into. So today, I'm going to talk about classification techniques now. Is it different kind of supervised learning technique? Okay, and here I will talk about k nearest neighbor. What are the different distance measures that you need to use in different situations depending upon the nature of the data? Then I will talk about some efficient version of k nearest neighbor called condensed k nearest neighbor, and then followed by another classification technique called logistic regression, if time permits, of course. And the logistic regression is something which is the fundamental for modern deep neural networks. Okay, so essentially you use logistic regression curves, bunch of collections of things to build modern deep neural networks. So I will cover those things in great detail, and then I will show you how you can basically optimize these parameters, optimize these objective functions to get the parameters and so on. Okay, so that's my plan today. Okay, so let's see how far we can go with this. So let's start with classification. Most of you know what is classification, but just for the sake of completeness, I will give you very quick kind of overview of that and then get into methods. Okay, before I move on, I have these two warm-up questions for you, because this is all about taking decision which particular supervised learning you want to take. And we had a discussion last day, but again, just as a recap, you can do this. First question, for the fast data, what kind of classification you want to, what kind of supervised learning you want to use?
Regression.
Okay, all right, this is regression. And for the second question, for the second data, what kind of supervised learning you want to use?
Classification.
Yeah, okay. So because from the level, the output level itself, you know that which particular supervised learning you need to use. That's the first decision when you are actually implementing things you have to make. Okay. And as we move forward, we will see other examples later on. But these are some of the simple examples just to illustrate the points. All right. So again, what's the nature of the training data? Because supervised learning, we always use training data. So the nature of the training data will have two parts: the features, okay, for all the samples, and the output level, something that you are interested in. Okay. So this is typically in a tabular form, something like this. And feature could have many things like numerical features, the categorical features, and nominal features, and all kinds of stuff. Okay. So just to fix my terminologies, in case I use different things while I am speaking. So when I will mean a single sample means the entire row. Okay, like all the features for that. And when I talk about the input features or input variables, that means the features of this particular sample. So here, for example, if I say single sample with sample ID 1, it means that in the first row that the age is young, head job is yes, and this output is basically up to below yes. Okay, input feature means the young and yes for this particular example. Okay, so that's how basically I'm going to use my terminologies. Okay, now when I refer to test data, we assume that we do not know the output level, but we know the features. for that particular sample. We are interested to predict the output levels. Okay, so for all test data, that is our assumption. Okay, and for all training data, we know that what are the output levels for all the samples. Okay, all right. So this is the kind of the basis of the this structure of the data for classification. All right. Now, quickly, couple of examples, simple examples. Think about image classification. The data typically you have in this form. So you have a set of images and their corresponding labels. So labels here could be the flower, the car, or even you can fine tune also these things, categorize the flowers into different categories depending upon the name of these flowers and so on. And for the test data, you could actually, you see the image and then you have to predict what it is actually, whether it's a car or it's a flower. Now, again, there are various types of training data, the way that you create the training. Sometimes for some data sets, you have the explicit features. Okay, something like the loan data set. Okay, where you have explicit features. That means the data is already in tabular format, in table format, and you just apply directly your classification technique. But in other cases, in fact, in most of the cases now, you have the raw training data. For example, you have set up images and then you have the labels. Okay, it's flower, this is car, or you have set up, say, documents, articles, text articles, and you have, say, label something like this is sports, this is medicine, or something like this. So these are called the implicit labeling. And when you have tabular data, you call it explicit labeling because you have the explicit feature engineering and so on. So we have to deal with both the situations. Okay. All right. So then how to basically use training data without explicit features? By explicit features, I mean you do not have the data in tabular format. You do not have the exact values of these features. Okay, often when you have the image data or you have, say, speech data or you have, say, video data or you have, say, textual data, we do not have the explicit features. You only know that we have the whole thing and you know the label. So there what we do, you basically, have the raw training data. You use some kind of feature extractor. This is another module in between. Okay, feature extractor will extract some useful feature. Okay, and it basically going to create fixed dimensional vectors or tabular format, and then you take some classification algorithm and then you use it. Okay, so that is the kind of the setup for most of these classification algorithms that we know. And the feature extractor will depend on many things, like you can use the human knowledge. Somebody can tell us that, okay, you can use this particular thing to extract features. Nowadays, what deep learning modules actually do, they basically automatically extract the features. So the feature extractor is already a part of these deep learning models. That is why these models are very attractive. But many other older machine learning models, something like decision tree, k-nearest neighbor, some support vector machine, and so on, in most of the cases, we explicitly assume that we have the features ready with us. If we do not have that, we have to use a feature extractor to get the features, and only then you can apply. Okay, so that's the more or less the pipeline when you have a training data without explicit features. All right, now let's get started with our this classification algorithm called k-nearest neighbor. Okay, and this is one of the simplest and yet very effective classification technique. Okay, and it is also a non-parametric. You remember that I remarked yesterday that there are models which are parametric, there are models which are non-parametric. Okay, so before I get into the actual details of k-nearest neighbor, let me tell you slightly detail that the distinction between the parametric models and non-parametric models. Okay. So in parametric models, so the models will have the model parameters, a set of parameters. Unless you estimate these parameters using training data, you cannot move forward. And I will give you some examples. A classic example is the linear regression function that we have seen. You know there are a bunch of parameters, theta 1, theta 2, theta 0, theta 1, theta 2, and so on. So this is an example of parametric model. Okay. Now in non-parametric model, you do not have such parameters. You can have some hyperparameter, The hyperparameters need not be estimated from the data itself. You basically have to set either by experimentation or something else, but you do not have the model parameters. Okay, so the k nearest neighbor is an example of non-parametric model, and you get to know why this is the case. All right, so here is this very simple algorithm, and it's very effective. There are problems with this one. You get to know what are the problems, but its simplicity is actually very well kind of documented. So what's the basic idea? The basic idea is, and this is an old saying, that if you want to know someone's character, okay, look at his neighbor. That's the basic idea behind this classification. Yeah, classifier. So if it walks like a duck, then it is likely to be a duck. So the feature is essentially using here that how a particular species is walking and how it is actually quacking, and then basically from this you can say that whether this is going to be a duck or not. So here's a pictorial example, something like what we typically do in k-nearest neighbor. So you have training records, for example, of different things, and we have a test record, and we have to basically label this test record. So what we do, we first compute distances between the test record and all the training records. Okay, that's the first step we do, and because we are going to use the k-nearest neighbor thing. And then what we do, then basically choose k of the nearest records based on the distances. Something like what you have seen in case of locally weighted linear regression or regression. Okay, so you wanted to use the k nearest neighbor points to figure out the model, and here basically you choose k of the nearest records, and then depending upon their levels, you can figure out what is going to be the level of the test record. Very simple idea. Okay. So the basic idea is, this rule is that the test samples level is the majority category level of its k nearest training samples. So if you have k nearest training samples, from these samples you see which of this category is in majority, okay, and then that is going to be the level for the test sample. Okay. Now in practice, k is usually chosen to be odd. Okay, k will, of course, k will vary. There is no very specific concrete guidelines of how one to choose k. Okay, it's difficult to do that. There are some shallow guidelines which I will tell you. So k is usually chosen to be odd so as to avoid ties. In case you have ties between two categories, so you basically want to break that tie. And by definition, when k is equals to 1, that means you are only choosing the closest neighbor. This is called the nearest neighbor classification rule. Okay, instead of k to higher than 1, you basically choose the closest neighbor, and depending upon that, you can simply say, okay, this is going to be my level. Okay, so just quick, yeah, please.
Can you explain the rule?
The rule, k-nearest classification rule.
Yes, sir.
Okay, so it is this, that say you are the test sample. Okay, I do not know your level, and there are lots of training samples in the data. So what I do, I will first compute the similarity between you and all the training samples, and then I choose k closest training sample based on the distances. Okay, now I know what are the k closest training samples. Now in this set, the k closest training samples in this set, I will figure out that which category is in majority. Okay, whether this is duck, whether this is say bird, whether this is flower or something like this. Okay, so in this case I said which category is in majority, and so my level would be that. The level of this majority category in this k-nearest neighbor set.
Okay.
All right.
Sir, can you elaborate why k is taken as odd?
So k is taken typically odd because just to avoid ties. Ties in the sense that, so for example, you say k is equals to 4 and you have 2-class classification, for example. Okay. Now k is equals to 4, 2 class classification. Now in this set, the closest nearest neighbor set, that from negative class you have 2 samples, from positive class you have 2 samples. So this is going to be tied. So then how do I decide that which category I am going to be in? That's the problem. So basically you want to break that. So odd number is actually better suited than even numbers. Okay, but still tie can happen. Okay, it doesn't guarantee that tie cannot happen. For example, you have 3 categories, and then say for example in your value k is equals to 7, then it can happen that 3, 3, 1. So 3 from one category, 3 from another category, and 1 from another category. Okay, so 3, 3 basically tie, their majority. So that can also happen. This doesn't guarantee that this tie will never happen. But in some cases, at least, for example, in particular, when you have binary classification, then you can basically tackle this problem. Make sense?
Yes.
Okay, all right.
Sir, I have a question.
Sure, please.
Sir, in the case of locally weighted regression, we have seen that the solution 2 was better. We did not take the means k nearest neighbors that time. So now in this case, can't we do like that? Using weight, we are downplaying the role of the other neighbors, distant neighbors.
Yes, in fact, in my slides later on, we have the distance weighted k-nearest neighbor as well. Yeah, that we can do. Couple of slides later, I am going to talk about that.
So this KNN method will be independent of scaling, right?
No. So independent of scaling means what? Scaling of features.
Yes, so like even if we like minimize or maximize the graph scale, then the k nearest neighbors wouldn't change.
So k-nearest neighbor depends on the distance metric that you are using. Okay, so any particular distance metric. There are many distance metrics you are going to know in a couple of slides later.
Okay, sir.
So it depends on the particular distance metric that you are using. If the distance metric is not taking into consideration the scaling issues, then there is going to be a problem.
Okay, sir.
Okay. Okay, all right. Okay, so next, so this is the kind of the pictorial view of the nearest neighbor space. So the cross is the test sample, and then the plus and minuses are the training samples. So plus means plus category, minus means minus category. And so when you have one nearest neighbor, so you know this thing, basically you are only considering only 1 point. When you have 2 nearest neighbors, you are basically considering 2 points, and so on and so forth. When you have 3 nearest neighbor, you are considering 3 points, and so on. Okay, so this is the very simplistic view of this space. All right, now one of the students asked me about this. So this is exactly the thing: the distance weighted k nearest neighbor. Why cannot we simply? Why we are really considering this thing, and why not distance weighted k nearest neighbor? Okay, so here is this definition. So in the original case, the previous case, we are doing this thing on. So this is just like the slightly different terminologies I will explain. So you look at this, the top one is the original definition of the k nearest neighbor, and the bottom up is this one. So let me just introduce the terminologies and then I will explain. So in this case, this is the level of ith nearest neighbor. Okay, the assumption is that you have already computed the k nearest neighbor, and then I'm trying to figure out the level for sample q here. Q is my query sample on the test sample. Okay, so if xi is the level of the ith nearest neighbor, then delta is a decision function kind of telling whether the v and fxi is equal or not. If it is equal, this is 1. If they are unequal, this is 0. Just like that. Okay. Now this is the distance measure between xi and xq. Xq is the feature vector for the test sample, and xi is the ith training sample, the closest neighbor. So this is the distance. So because we really want to use the distance as a kind of the points which are far apart from one point will be downweighted. So this is the kind of inverse thing that we are using. And then v is the set of labels, all possible labels. and this is the predicted levels for the test sample. Okay, so same thing that we are doing, but slightly different way representation. So you are essentially taking the argmax V belongs, small v belongs to capital V, essentially telling that which level is in category majority and nothing else. Okay, and here we are actually using the distance. The only difference is that the distance d now is being used to downweight the samples which are far apart. So what is the advantage of this one? The advantage of this one compared to the standard hard k-nearest neighbor. In hard k-nearest neighbor, what we have been doing, that once we figured out, okay, this the k set or the k samples are my closest, we simply go and take the majority vote. Okay, so if the distance between me and my closest sample is 1, and if the distance between me and another sample is 10, they are being given equal importance, because only because they are within my k-nearest neighbor set. Okay, so this distance weighted thing, okay, is basically considering that particular aspect, trying to address that problem. Okay, any question? Do you have any question on this?
So that left hand side f hat is a vector.
Sorry.
That f hat on the LHS, is that a vector, sir?
No, this is not a vector. This is the predicted level for the test sample.
No, like why is that symbol hat on the top?
Oh, hat is basically you are estimating this. That's what you are predicting this. This is not the true level, but predicted level. So in machine learning, you always use this hat kind of thing just for prediction.
And sir, please explain again decision function.
Oh, decision function. Oh, okay. So this is okay. All right. So say B is one category 1, for example. Okay. So capital V is the set of all possible categories in your data. Okay. So if you are dealing with your loan approve data, right? That you have seen, there are 2 categories: yes or no. Okay. So the capital B will have yes or no, and small b is basically taking all these values. So the delta B f of xi is basically checking f of xi is the level, the true level or the training true level of ith sample. Okay, ith training sample, and B is the one particular the level. Okay, so it's checking whether f of xi is equals to V. If they are equal, then delta is returning 1. If they are unequal, delta is returning 0. So it is basically counting that how many samples from each category you will have in k-nearest neighbor. That's what it is doing. Okay. Any other question on this?
Sir, so you're saying the value of B will change from neighbor to neighbor, sir?
Yeah. Value of D.
I mean V, sir, V. Like, is that the marker of either positive or negative a neighbor?
So you mean the capital V or small v?
The small v which is inside the delta function, sir. I mean the decision function.
Okay, so a small v basically set up all possible categories that you have in the training data.
Okay, sir.
Okay.
So, like basically we are using that delta functions to calculate 1 by d square for each label separately.
Right, exactly right. So in the argmax telling you that, okay, which category is dominating. So it's like you basically take one level, then compute how many samples are there in the top K, take another level and do that, and that's it. Yeah. It's basically counting that how many levels, how many categories that you have in top K set. Okay.
Sir, why are we here then considering only k nearest neighbor? Because if the weight is downplaying the role of the other neighbors, like why can't we consider every neighbor?
Okay, so there are two possible reasons, two reasons for that. Number one is that even though we are using distance as a kind of downweighting factor, so in practice, when you have like very dense data, okay, and large data, then if you basically going to sum up the whole thing, like the taking all the samples and so on, so the performance is not actually very good compared to if you kind of take the hard cut of K. Okay, so that is people have actually empirically seen that. Okay, that's going to be a problem. And the second reason is that if you are going to consider all the points, if you have a large data set, then you have to compute distances between all the points, and then this is going to be problematic because k-nearest neighbor itself is very time consuming. So you can use some kind of approximate k-nearest neighbor search to figure out only top k.
Sir?
Yes.
The function f, right? So how do we get that? Is it already given to us?
So, okay. So function f essentially telling that what is the level of the output level of xi.
So
Yeah,
in real data, we don't have function, right? It's just given to us, the label.
In real data, yeah, we do not have, I mean, at least we do not know, yes. Yeah, right.
Sir, in the previous argument, you mentioned that in the second point, you mentioned that we have to compute distance for every pair. That's why we don't use for all, and we use it only for k nearest neighbors. But in order to find k nearest neighbors, we have to compute for all the pairs, right?
So yes, but there are some approximate k-nearest neighbor search, and I tell you how you can do this. Again, I'm telling you this in approximate. Okay, so say you have 100 training samples. Okay, I'm just giving an example, and then you want to figure out say 5 nearest neighbor out of this 100. So one possibility that you mentioned, you just go and compute distance between like this test sample and all 100 samples, and then basically do it. That's a perfect way of doing things. Now in approximate nearest neighbor search, what we do, we can kind of do some kind of clustering of the training samples. So if you have 100 samples in your training data, we can create say 5-6 clusters. Okay. So say assume that you have created 5 clusters. Okay. So each cluster expected that will have similar kind of samples. Now for the test sample, what you do, you can actually see which cluster centroid is the closest to your test sample. So there you only need 5 computations, or 5 like computation against only 5 centroids or 5 vectors. Okay, and then you take the top one and take all the samples from this top category, and you can reduce this computation. So that is of course the approximate k-nearest neighbor search, not the exact one which you otherwise get if you use all the samples. Does this make sense?
Sir, essentially the function for all categories, we is trying to find the max frequency guy, like which is nearest to f of xi, or sorry, nearest to v.
Which function you are talking about?
This f hat of q, sir. What is it finally giving us?
Oh, AF hat of Q is basically the level for the test sample Q. So you see, ultimately you have to predict the level, right, for the test sample Q. Q
Yes,
is your
sir.
test sample.
Which category it belongs to? We need to find that.
That's the category. Yes.
Yeah. Sir, what is the format of v, sir? Is it a vector? V and f of xi, are they like vectors?
V means the small v or capital V?
The small v, sir, small v.
No, this is basically the categories. So if you have say.
So I mean, if you say if you have sample where we have 2 classes, sir, like 0 and 1. So then what is v here? Like say the plus is 1 and the minus can be a 0. Then what is the v here in this case?
So V is basically, the capital V is basically set of these all levels 0. So if you have 2 categories 0 and 1, then the capital V is basically the set consisting 0 and 1. And small v essentially taking one of these values from these categories.
Okay, sir. Okay.
Okay. And X is basically are the feature vectors for the sample. Xi is the feature vector for ith training sample, or rather the ith closest neighbor sample, and Xq is the feature vector for the test sample or the query sample.
So I mean, sir, like simply like v is a number, right? In this case.
Yeah, v is a number. I won't say number. So it depends on the level. For example, yes, no kind of example, which you have seen, right, in the lone data example. So v here, yes and no. Okay. Now, if you consider an example like say document classification, okay.
Yeah, I mean, like we can't use it yes or no for like computation, right? Because for the decision functions, we can't use like classes, right? We had to have some kind of representation for them, right? Numerically.
For k-nearest neighbor, you do not have that problem. For other places, you can have problem. You have to basically convert this in numerical quantities. But here, you just comparison. So symbolic things is not a problem here. Okay, but if you think about representing these things in computer's memory, of course, then everything needs to be converted into numbers. So yeah, in that sense, yes, right.
Okay,
So
sir.
does the output of the term after summation, including the summation, would it be like a matrix or would it be a scalar quantity? Because there is a maximum and argument term in front of summation symbol.
Okay, so you take out the argmax part. Okay, let me just break these things into smaller parts and explain. You take out argmax part, right? Just take that out. Okay. Now take one category, say 0th category. B, small b is equals to 0. Set that. Take argmax out of this expression. What you are going to get? You are going to get a scalar quantity from the summation. What it is telling? It is telling that in the k-nearest neighbor set, how many samples are from, say, that category, say 0 category. Okay?
Yes.
Does this make sense?
Yeah, yes.
Yeah, then you can do for other sample. That's why this argmax is like a for loop. Okay, for all some like levels in your data. Make sense?
So then we can simplify that into double summation, like v equal to 1 to number of different classes, and second summation includes like I equal to 1 to k.
So you can do that, but ultimately you have to take the maximum of this. No, that's why I said argmax. So argmax is like very standard.
Okay.
Use. You have to take the maximum out of it, right? Because ultimately you want to produce the maximum the level of the majority category. That's why I said argmax. This just shorthand.
Yes, sir. Got it.
Just shorthand here.
So we are calculating the summation for every label in set capital V and taking the max finally.
Right.
Okay, sir.
Yeah. So this argmax thing is probably you will encounter many times in machine learning literature, because this is something basically it's a shorthand for this. So you will probably encounter many times here and there. That's why I'm just using that.
Sir, here k is a hyperparameter, right?
K is the hyperparameter, yes, that's true.
So, sir, how to know about the best value of k?
Well, I think you never know best value of k. That's the problem. There are some guidelines, and I have one guideline in the next slide, but you never know what is this good value. Hyperparameters are very difficult to tune. You just have to look at the data that you have. You do some kind of cross validation, running multiple times, and choose which is basically giving you some satisfactory results. But hyperparameters are always a problem, and you can never guarantee what is the good value of hyperparameter.
Okay.
Okay. You can just follow some guidelines, but that doesn't guarantee that you are going to get good things. Okay, all right. So yeah. So next is that. So in this slide, we are talking about the kind of this the classification thing, right? The discrete levels. Okay, the levels that you are predicting discrete. Now there is no reason that we cannot extend this whole thing for the continuous values features. Okay. Now this is not on classification thing, but on consider this as a regression thing. So it is essentially telling you that the regression using k-nearest neighbor, how you do it. Okay. So in classification, what you can do basically, you say for example f of xi, again the same thing, the output level or output value for the sample ith sample, and here the wi is the weight for that, and so it's basically normalized weighting that you are taking based on the top k nearest neighbor. Okay. Just simple modification of this formula, same thing. Okay. Now, what are the issues? Very simple. So in fact, for many learning algorithms, people use k-nearest neighbor to understand the behavior. So deep neural networks, as you know, very difficult to understand. Okay, it's like a very big black box. Now, what people are trying to do now, they are trying to understand the behavior of deep neural network using k-nearest neighbor classifiers. Okay, you take out some features out of deep neural networks. You basically look at the nearest neighbor and try to understand what is happening. So this is actually a very good classifier to understand what is happening. Okay, because of the simplicity and because it's parameter free, apart from k. So the issue, of course, the unresolved issue that we all face, the value of k. Nobody knows what is the good value of k. Okay. Second issue, of course, the kind of distance metric that you are using. Okay, again, there are scaling issue, there are heterogeneous data issue. For example, some attributes are continuous, some attributes are discrete, and so on and so forth. So those are the issues that you have to figure out. And then, of course, the computational complexity issues, which I briefly mentioned in the last slide. That it depends on the size of the training set. And also, when you are computing the distances between two vectors, it will depend on the dimension of the data. Okay, if you're computing Euclidean distance, for example, if the dimension is very high, then you are going to take lots of time to compute the distance. So these are the some of the issues, okay, the main issues for k-nearest neighbor classifier. Okay, so choosing the value of k. Now, as I am saying you that there is, at least I do not know what is this the value of k which will guarantee some 90% accuracy or so on. At least I do not know that. So instead, what I'd like to tell you is there some guidelines. Okay. So guideline is that if k is too small.
Hello.
हाँ बोलिए ना आंटी.
ठीक है ना?
हाँ हाँ सब ठीक.
Can you please mute your microphone?
तो बोलना बात करने के लिए.
हाँ हाँ.
बुखार ठीक है? नहीं चढ़ा रात में बुखार?
नहीं नहीं.
Only you can
mute your microphone.
ठीक है, उधर जाना तो बात करवाना ना.
हाँ.
ठीक है.
Sir, you can mute him, sir.
Okay. So yeah, okay. So if k is too small, then of course you are sensitive to noise points. Some outliers might be there in the data, and if k is too small, you are relying on small number of samples. So that's basically the outliers can dominate the class levels. Now, if k is too large, essentially you are basically enlarging your space, nearest neighbor space, and so distant points may get included into the set, and that's again it can basically distort the class levels and so on. So not very helpful guidelines, but what you should do in a situation like this. So rule of thumb is that, and this is the rule of thumb is that, so k is typically, and this is actually the upper bound, k should not be higher than square root of n. Okay, so that's the kind of the rule of thumb that people suggest, where n is the number of training points. Okay, so you can choose maximum value up to square root of n.
Sir, what is the meaning of sensitive to noise points?
So say you have, by chance in the data, say for example you have some outliers, okay, some noisy level data, okay, some data because of some noise that it was erroneously labeled as, say for example, yes instead of no. Okay, now if that is the case, then like if you take only one point, by chance if that point gets included into your nearest neighbor, then you are basically going to label it erroneously. Okay?
Okay, sir.
That's what I'm referring to. So because in real data, noise is very common. Okay, so that's the problem. All right. Now here are some of the distance metrics. This long list of metrics that we use. So mean Kawasaki distance. I'm not describing everything in detail. Just like it's the formula, you can very easily, I think, understand. I'm just quickly run through it, and if you have any question, I can take it up later. Okay. So assuming that we have the two feature vectors x and y. Okay. So indexed by xi and yi, and we want to basically compute the distance between two vectors. Okay, of dimension m, of course. So mean Kawasaki distance you basically can take, or the r is a like parameter. Then Euclidean distance, most of you know, is basically square distance. So and then is a special case of mean Kawasaki distance, of course. Then you have Manhattan distance. We simply take the sum of the modulus. Then there are lots of distances, like you have the quadratic distance, where there is one matrix called Q, which we learn from the data depending upon your requirement. So if you have a particular requirement from a particular data, then you can actually learn this positive semi-repeated matrix Q to compute that. Mononomial distance is another interesting distance measure, but it's computationally complex because for this you need to compute V and V inverse, okay, which is basically the covariance matrix of all the like these column vectors, okay. Then you already know, I think, the correlation coefficient, the chi-square, the Kendall rank correlation, and this and that. Okay, so these are like a whole list of distance metrics that you really want to use. Okay. Now, one of the questions that was asked a little while ago, that the scaling effects. Okay, so different features may have different measurement scales when you are getting the raw data. That is what actually happens. Okay, something like patient weight in kilogram. You have the patient features, and you want to basically use that data to kind of predict health issue or something like that. So we often take the patient weight, which is in kilogram, and say we also recorded the blood protein values, okay, for the same patient, and so that is in nanogram actually per deciliter. So the values are basically, the ranges of these values are very different, okay. So as a consequence, if you straight away use this thing into your distance measure, then in this case, of course, the weight feature is going to dominate the final distance value compared to the nanogram for blood protein values, okay, because that's a smaller number. So those things is basically problematic if you do not address this thing scaling effect appropriately, okay. So a simple solution for this is standardization, which is basically you can transform the feature values into z-scores, okay, by kind of you compute for every column, you can basically compute the mean of that, okay, and then you can compute the standard deviation and simply do this transformation. So original value minus mean by standard deviation, and you can basically scale these values to kind of tackle these problems, which is like very standard transformation rule. Okay. Now we talked about distance metrics, etc., etc. Now, what happens when you have nominal attributes? Okay. So by nominal attributes, that I mean that the attribute values are symbolic in nature. Okay. Don't confuse between nominal attributes and the discrete attributes. Discrete attributes can be numerical. Okay. For example, the age. Okay, in years, for example. Okay. So they are discrete, but they're numerical attribute. So nominal attribute is the attribute which has the symbolic value. Okay, something like color. Okay, something like that. So if you have nominal attribute, then one of the measure that you can use to compute the distance is called value difference metric. And again, this is defined as this, precisely defined. You can just take a look into it. So NAX is the number of times attribute A had value X, a particular value X. Okay, so you basically go by attribute and so on. Capital C is the number of output classes that you have in your data. Similarly, NAXC is the number of times attribute A had value X in a particular class C. Okay, so just like from this definition you can quickly get it. Okay.
Sir, what are nominal attributes?
Sorry?
What are nominal attributes?
So nominal attributes is the attribute which has symbolic value. Okay, for example, the color. Okay, so you have the symbolic values.
Got it, sir.
Okay, all right. So now let's consider another situation, realistic situation, and in fact we encountered this situation often. It is so distance for heterogeneous data, and by this what do I mean is that in any real data, I think you probably encountered this situation now and then, that the attributes is a combination of continuous valued features, discrete valued features, nominal features, and so on. Okay. Now, of course, you cannot use the standard distance measure to do that. So another kind of well-known distance measure is called HVDM. Okay, it takes again two samples with m attributes and then tries to compute the distance between these two. So what it is that? So there are three possibilities that if one of these attributes is actually unknown, Okay, that is missing. So you can basically say 1. If it is a nominal attribute, then you can use this previous definition in the previous slide to compute the value. And if it is a linear attribute, okay, or numerical attribute which you can order, then basically you can use the normalized difference like this, the absolute difference normalized by the values and to get it done. Okay, so this is the kind of things that you could do when you have heterogeneous data with heterogeneous features. Now, just to wrap up, in nearest neighbor, 3 broad issues. First of all, we already discussed this is an expensive thing because you have to basically determine the training sample, the nearest neighbor using from the KA training samples. Okay. So one of the way that you could actually handle the pre-short training examples into fast data structure. One of the data structure that is very popular for approximate near neighbor structure is called KD tree. So it's a tree-like data structure, okay, on the high dimensional space. You can basically use the data, something like binary search, the B tree or binary search tree, okay, something like that, but on high dimensional data. So you can organize your data using a tree and then basically use that tree structure to quickly figure out some k-nearest neighbor, okay. People also use locality sensitive hashing, okay. So to kind of figure out the approximate distance between two feature vectors, okay. And the other way to do it is the remove redundant data or condensation technique. So you can actually compress the training set into smaller set, which I think you think like good for my classification thing, which we will going to see in a moment in great detail. Second part is the storage requirements that you must store all training samples P. Okay, so because for large data this is going to be a problem. So where do you handle it again? Condensation, that you only keep the required samples which is necessary for good classification performance. Okay, or you can basically pre-sort the whole things using some kind of tree. Third problem is high dimensional data. By high dimension I mean the number of values in a particular sample is very high. That number of features is very high. Okay, so typically you need more training data if you have higher dimensional data. Also, you know that you have to compute the distances between samples. So computation is going to be costly because of the number of features is higher. Okay, and so therefore, and then again the partitioning techniques degrade to linear search in the high dimension. If you partition the data, try to partition the data into several things, something like the clustering techniques and that you apply, then it's basically essentially kind of linear search in high dimension. If dimension is very high, this is going to be problematic. So how we can reduce then the computational complexity? Okay, so one way to do it is reduce the size of the training set. Okay, so condensation or editing. If you have say plenty of examples in your training set, now can we do something to keep only the necessary samples which I think is good for my classification performance? Can we figure that out and do that? Okay, so one way to do that, of course, which I mentioned, some kind of data structure KD tree, which I mentioned briefly. You can use that one, but we are going to look into separate another machine learning algorithm to do that. Okay, so the idea that we are going to now talk about next is called condensed k-nearest neighbor. Okay, that is the approach. Again, it's machine learning approach. Okay, algorithmic approach to figure out the condensed k-nearest neighbor. Okay, so I think we take a short break and then come back and then start talking about this condensed k-nearest neighbor.
Hello, sir.
Please.
Sir, in the previous slides where there was decision function, it will only take value 0 or 1 or something else like.
In which slide?
In the previous slides in the k-nearest neighbors where there was decision function.
Delta.
Yes.
You mean delta?
Yes.
This returns the value 0 or 1. just a Boolean function.
Okay.
Okay, so we are back. I hope you can hear me.
Yes, sir.
Yes, sir.
Okay, thank you. Okay, so let's get into condensed K nearest neighbor. And before I get into the algorithmic details, so the main objective, of course, to kind of reduce the complexity, the time complexity rather, of K nearest neighbor classification. Okay, so you want to do it fast. That's the main issue that we are trying to address. So so if you look at, for example, the kind of things that you have been doing, we can actually break the, so you can think about that the points are on space of some n-dimensional space. So there are n-dimensional feature vectors, and so the entire space can be divided into several regions. Okay, small regions. So here you can think about a single region. So each cell here, okay, each cell one sample, and every location within the cell is closer to that sample than to any other sample. Okay, so this is also called the Voronoi diagram. So it essentially divides the space into several segments, and you can think about the one particular segment will correspond to kind of the nearest neighbor for one sample or category and so on. Okay, so what we are trying to do in this case is that the knowledge of these boundaries, if you can somehow figure out, okay, what are these boundaries actually, okay, so some samples or some examples, training examples that will help us to figure out those boundaries actually, then we are basically done. We do not need to keep all the samples. Okay, so a particular region may contain 10,000 examples, but those all 10,000 examples are not really required to know the boundaries. So if we can have say 5, 6 or 10 points, which will be enough to know the boundaries, then I'm basically done. Okay, so I only can keep those boundaries, those points for determining boundaries, and then basically I can go and figure out, okay, what would my class levels and so on. So here is this basic idea of condensing. Okay, the objective is to reduce the number of training samples. Okay, so we want to kind of we have to discard the redundant samples from the data. Okay, so you return only those samples which are needed to define the decision boundary, that we have seen something like this. So two quick definitions for this. One is called the decision boundary consistent. So what is that? This is a subset of samples whose nearest neighbor decision boundary is identical to the boundary of the entire training set. Okay, so those points, like which if you basically use those samples, and the decision boundary generated by those samples is equivalent to the decision boundary of the entire set. And the minimum consistent set is the smallest such subset. That's the smallest number of examples that you can basically take, which will give the decision boundaries. That's what we do. So here is an example. You have this original data here on the left side. So it's a 2-class data, okay, and you can see here is a basically condensed data that you have. There are condensed data you have. There are 7 points, 4 from the red category, 3 from the blue category, okay, and there you have the minimum consistent set. Okay, only 2 points will be sufficient to get the decision boundaries. Okay, so our objective would be to figure out the right part. We may not be successful always, but that's the objective. But again, this is going to be an approximate algorithm to figure that out. Okay. So here is this algorithm, very simple algorithm. Okay, we call it condensed nearest neighbor, short from CNN. Don't confuse with the CNN for convolutional neural network. That's a different thing. So what is that? So it's basically a 4-step process. So you have a bunch of samples, training samples, and we want to basically condense it. We want to keep only a few samples which will be helpful. So what you do initially, you initialize a subset with a single training example. You just randomly choose a single training example from your data and put that into a subset. Yes, and this is the subset we are basically going to grow, and this is the subset we will finally produce. Okay. Now what you do? Now classify all remaining samples except the one that you have accepted. Okay, here the red circled point, you accept that, you take other samples and you try to classify that samples using only the subset S. Do not use the other examples. The subset S is going to determine you the class levels and nothing else. Okay. So then you basically apply one nearest neighbor rule. Okay. And then transfer any incorrectly classified samples to the subset S. Okay. So the points which you could actually classify correctly using subset S, you discard those because you already know the subset is actually sufficient to get that information. Now points which were not able to classify correctly, you basically include dash points into S. Okay, and you basically repeat until you see there is no change in the set S. Now let's look at the example. The example probably will try to explain the things slightly more detail. Okay, so this is my the points, whole points, and my first step I had chosen the sample with red circle mark because I have to initialize the set. So that is basically my yes at the very first step. Now what I do? Now I will apply step number 2. Okay. So here what I do is that now I have to basically choose other points, okay, and try to classify them, okay, using set S only. So here my set S is only this one. Now I have to consider all other points, okay, and then if any point which is being misclassified will be included. So you remember that because there is only one point into set S, this particular set S, there is only one red point here. So all these points like red points will be classified correctly, okay, because there's only one point in it. Now all the blue points will be classified wrongly. It's a trivial case, right? And because you are choosing these points in any order, the order you do not know yet. So, for example, you had chosen this particular blue point first, okay? And so you know that there is only one point in set S. So there is a misclassification. So basically you have accepted this one into set S, okay? So now my set S will have 2 points, this particular point and this particular point. Any question? That is important to understand.
Sir, what is meant by misclassification here?
Okay, that's a good question. Okay, misclassification means that your set is only S, as if your training set is only S, right? Now this is the set you have, set S. The misclassification means, say for example, you want to classify this point using this set S. S will have only this point. Now you simply like compute the one nearest neighbor, okay? One nearest neighbor you would apply, one nearest neighbor you apply, and then see what is the level of the one nearest neighbor from the set S. If the true level of this sample agrees with the one nearest neighbor level, then this is a right classification. If they disagree, then this is a misclassification. Make sense?
Okay.
So, for example, in this case, trivial case, now let me just go back to the previous slide maybe. Yeah, okay. So when you have set S with only this point, then all the red examples will have no problem. That's the correct classification because there is only one sample in the test set S, training set S, and so you can basically, it's a trivial case. All red samples will be classified correctly. That is not a problem. But on the other hand, all green samples will be misclassified, right? So in step 2, I have to apply. So in step 2, you can basically choose any of, because in which order I am choosing these things, I do not know. And just, you can basically choose one point and then basically misclassification. So my set S will contain now 2 points, this and this. Clear?
Sir,
Yes.
one question.
Yes.
Why?
Yeah, please.
Why there will be only 2 points? Because all the blue points will be misclassified.
Yeah, so I'm just going. So this is the after the first computation. So I will gradually go and progress here. I'm just showing the immediate next thing, right? Next step. That's why.
Okay.
There will be multiple points.
Sir, can you explain again, sir? Second point. Step 2.
Oh, second point. Okay, second point. Okay, all right. Now let me just go back to this slide and explain. Okay, so let me just ask you this question. So is it clear that this point is basically yes? Do you have any problem there?
No, sir.
No problem. Okay. Now what I have to do, I have to apply step 2. That will classify all remaining samples using the subset S. That means subset S will be used to predict the level and nothing else. And you apply only one nearest neighbor rule. Okay. So what you do, basically you say, you choose this point, say this point, particular point you choose. Any point you can basically choose. You have to basically do this thing. So you choose this point, and this is your set S. So you compute one nearest neighbor. There is only one point in it. So the level of this particular thing will be the level of the red sample, right? Is it clear to you?
Yes, sir.
Okay. Now, because the level of this based on the set S, you are saying the level of this green point, one where the mouse pointer is, so is basically the red. So this is a misclassification because in the original data you are saying this from a different class, right? So this is a misclassification. So therefore you have to include that into your set S. Now in the next step the point could be this one or the point could be this one. Any one of this point could have happened, but I have just basically I am choosing this point in some order, so I have basically included this one. Make sense?
Sir, now
yes.
Now, as you said, when we take this blue point and put it in the set S, like which already has a red point.
Right.
Now the blue point will be taken as a blue point or like a red point?
Blue point will be taken as a blue point with the true level. That's a good question. Yes.
So now then the set S will have two elements now, sir. Like in this instance.
Set S will have two elements. One from blue, one from red.
Yes, sir. Then in the next, like say in the next iteration of finding elements, then you have both red and blue in the set S. Then how do you even determine any point's color? Because both of them, they talk otherwise, right?
Both of them what?
As in like see now set S, like sir, now set S has both red and blue sample. So now when we go by detecting the other samples like true level, then because of the red point it'll say red, because of the blue point it'll say blue.
No. So I'm coming to that point because you are doing one nearest neighbor. You have to compute the nearest neighbor of between these two samples and then basically choose that one. Coming to the next slide, I'm coming to that.
Okay.
Okay. All right. So after this is clear. Okay. All right. So now my set will have these 2 points, this one and this one. Okay. So this point and this point my set is. Okay. Now what you do? You take samples, the other samples, and you apply one nearest neighbor from these 2 points, this point and this point. One nearest neighbor, only considering the closest nearest neighbor. Okay, the closest one, only single point. Now for this, of course, in this case, only for this point, the nearest neighbor seems to be this one, the red one. Is this clear?
Yes, sir.
Yes. Okay. Now this is a misclassification because your true level was green, but nearest neighbor is red because of set S. You are telling that is level is red. So it's a misclassification. So therefore you are including that into set S. Make sense?
Yes, sir.
Any doubt from anybody?
Excuse me, sir.
Okay, sure, please.
Sir, in the when you consider the first blue point and included it in the subset, you said that both are the same label.
Not same label. I said misclassification. So because it's a misclassification and you are putting that into set S, but when you are putting that in set S, you retain the original label, the true label. Make sense? Or you have problem?
Yes, sir. Yes.
Yeah, you do not change the labels. Okay, in the set S, the examples will have the same label as you had in the original training set. You are not playing with the labels, but you are only deciding whether you should include a particular sample into set S or not based on the misclassification thing.
So,
yes.
Sir, excuse me.
So like while selecting the second sample, like we selected a blue sample in a random order, right, sir?
Yes.
So sir, like luckily in this case, like a blue sample got selected, it was kind of like in the center of the cluster of the blue things.
Right.
So like every time it might not happen, right? No, sir. Like we might end up selecting a
Yeah,
very noisy data.
absolutely correct. Yes. So this is order dependent. Yes. Okay, that's why I said that this is an approximate thing. You cannot guarantee the right boundary because it depends on the order. You're absolutely right. So in the first step, this point could have been instead of this point could have been this one, right?
Yes, sir. Then there would have been more misclassifications in the red itself.
Different kind of classification. Yes, that's right. Yeah, that can happen.
So excuse me, sir.
Sure, please go ahead.
So in the second step, we have the set S containing the red one and a blue dot.
Right.
So while finding the nearest neighbor in the third step, does it go in order like first in first out? So initially we consider the set S to have only the red colored one. Then we consider we consider having a blue colored one. So first, is it a specific rule like we need to find the nearest neighbor for the red one and then go for the blue one, or?
Can you repeat your question, please? Last part at least.
So now the set S contains a red dot and a blue dot.
Right.
Initially, we added set S first. I mean, the red color dot first, and then a blue color dot.
Right.
And in the third step, that is the step currently on our slide. So we are finding the nearest neighbor for the red dot.
No, not nearest neighbor from the red dot. You are finding nearest neighbor from the set S. And set S has 2 points, one red and one blue. Okay, so you are finding nearest neighbor from the set S. And in this case, the nearest neighbor happens to be the red colored.
So then what about the misclassification part? Because in the first case, we thought that since there is one...
Yeah, okay, misclassification. So this blue one, now see, you have the original training data, right? Where you have the true levels. Okay, this is the blue are the blue levels, red are the red levels. Now consider this red, the mouse pointer red, and this mouse pointer blue is your set S. Now I am considering this point. Now for this point, the nearest neighbor from set S is red point. Up to this is clear to you?
Yes, sir.
Okay, all right. Now because of this, so my S set S telling that the level of this green should be red. Right? Is this clear to you?
Yes, sir.
Okay, but true level suggests this is actually green. So this is misclassification.
Oh, yes, sir. Got it.
Okay, and that is why I'm including it. Okay?
Yes, sir. Got it, sir. Thank you.
Okay, all right. So basically that's the step, and you follow this step again and again. So next what you can get something like this. Okay, it's another basically red point that you are going to get because of the distance. So nearest neighbor happens to be the blue one. It's misclassification. So you're going to include this and so on. Next step, same step you can apply. Okay, so then you are going to get in the next step something like this. Okay, now 4 points. Now in the next step, you are going to have this kind of thing. You have basically 6 points, 4 from red, 2 from blue, and so on and so forth. You can get another one and so on. Okay. So same thing that you can basically apply. Okay, that we have seen. You just repeat it, and you start when
Sir, why, any significance of the gray border? Like, why is it changing?
Okay. So this is basically showing you the current decision boundary based on the set S, how your decision boundary is actually changing. Okay, so that's what basically, nothing else.
Okay.
So we are randomly adding points into the subset, and then we are calculating the nearest neighbor and then classifying them, and then the decision boundary is being made subsequently in each iteration.
Not entirely randomly you are adding. So the first step, of course, you are choosing random points. Second step also you are kind of random because you are basically choosing 1 point from the samples, but then it doesn't become random. So for example, in this step, let me just look at this. So you are here, for example, right? You are here. Now you are not choosing random in a particular order. You can actually choose this one. Or yeah, you can say something like random order, something like that. Yeah, you were right, I think. You are right.
So sir, it's random from the misclassified labels. Sir.
Random from the misclassified. So no, the choice of these points, for example, it's in a kind of in a random order, right? So the points that you are choosing to basically classify using set S, that is in some order, random order. Actually, what you can do, you can actually order the samples at the initially, and then you can basically go and basically choose these points in that sequence all the time. That you can do.
So sir, we'll be choosing in that sequence, and as soon as we get any incorrectly classified sample, we would be adding that to the subset S.
Right, absolutely, yes. Because so here is the intuition behind it. So why I am adding the incorrectly classified samples, not the correctly classified samples. So set S is storing some information, right? And so if the samples are being classified correctly using set S, I do not need that sample in my training set, right? Because I am able to classify that point with the set S, which I already have. So why do I basically going to add that point? I have sufficient information in set S. Now the points which are being misclassified using S, then I know S is not sufficient, S doesn't have sufficient information to classify that point correctly. Therefore, I have to add that. That's the basic intuition.
Yes, sir, got it.
Okay. All right. So yeah, so in this way you just proceed in this way, and then you stop when you see the S is actually not changing. Okay, S is actually fixed, not changing into consecutive iteration or to consecutive step, and basically you can basically choose this one. Okay, but you said it depends on the order in which you are accepting the points, so decision boundary can be different depending upon in which order you are actually choosing that. Okay, so finally, from all these data points, so the whole this box is your original training samples, the whole set, whole universe that you have. Okay, you only reduce to these points. There are 7 points. Okay, so these 7 points, which is set S, is your condensed set, which you can basically use to classify any new data. Okay, that's why it's called condensed k-nearest neighbor. We will also call this edited k-nearest neighbor because you are editing this data to keep only the data which is required to classify correctly. Okay.
Sir?
Yes, please.
Once our set is updated, are we again classifying each and every sample according to the new set?
Yes, of course you have to do that. Not every sample, the samples that not part of S.
Yeah, means after we updated the set S, we are again classifying every samples apart from those elements in S.
Right.
To again get. So sir, won't it take so much time, as our goal here is to reduce computational cost for the KNN?
Okay, so yeah, good question. So let me answer. Okay, so this condensation or editing is a one-time job. It's just a pre-processing step. Okay, you have training sample, you apply once the condensed algorithm, you get this set with say 7 points, and you simply store it. Okay, so it's a one-time job. That's why, like, even if it is taking some time, it's not a problematic. But for testing new samples, there will be lots of test samples which will be coming in, okay, now and then. So you are basically going to test those samples against this set, which is now basically small. So that's the repeated event. That's why it is faster. Is it clear? Any doubt?
No.
No. So in general, in algorithms, any kind of computer algorithms, the thing that you care about is that if something is one time, you can probably spend lots of time doing that. If something where you need the repeated responses or repeated processing, that is where you need to basically speed up the whole thing. Okay, so that's why basically it's not such a big concept. Yeah.
Sir, while testing, will we use KNN, normal KNN, with the condensed sample?
Yes, we use normal KNN. Yeah.
Sir, then here we are using 1NN for the pre-processing, and then we will use KNN. So will the results be in sync? Because now for we are testing using the set S, right? So the set S has been found by applying 1NN. So for the KNN, will it give correct results? Means correct means good enough results.
So that's a good question. So the reason that 1NN was chosen is because the way this algorithm is actually working. Okay, so you can actually modify that algorithm. So initially, when you have a single point, you cannot do anything beyond 1NN. Okay, even when you have 2 points, you can probably cannot go beyond 1NN and so on and so forth. So in that sense, yeah, this is problematic. Okay, so but what would be the consequences of, that's a very good question. I have not thought about it. So what would be the consequences if you later on apply k nearest neighbor for any arbitrary k? I'm not very sure about. I will try to look into and then try to clarify in the next lecture. Okay. 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 So shall I move forward?
Sir, this method is just in helping in the computational part, right?
Yes.
But like if you consider how the algorithm works, like if you consider a point near this boundary, and and if you consider two nearest neighbors, so there'll be no, there'll be very few points. I'm just saying that there'll be very few points. So will that affect the accuracy of the test?
Yeah, of course, this is going to be. That's why I said this is an approximate k nearest neighbor. So this is going to definitely this is often worse than the original k nearest neighbor. Okay, because you are basically reducing lots of information. Yeah, that's true.
Sir, while classifying the test set, if we use 1NN only, then it will be more efficient, right?
So even if you are doing 1NN, then you have to basically compute the distances, right, between the points, all the points.
Yeah, but I'm talking like after we have done CNN step, like condensed nearest neighbor step has been done.
Okay.
And after if we bring some new data set, then if we use only or if we take 1NN, I think that would be great for classification rather than performing KNN.
Well, I think so I've already mentioned the risk with 1NN. Okay, because of this noise, outliers, some data misclassification, some noisy levels that going to create some trouble for you. So 1NN is generally is not a great idea unless you have the noise removal things and all. So, but because this condensed set was actually created using 1NN, in that sense, your approach is consistent with that one. It can avoid some of the problems that I at least know yet if you apply K for higher value.
Okay.
Okay. All right. Okay. So yeah. Okay. Now let's look into another classifier called logistic regression. Okay. And this is the foundation for, you can say like this, deep neural networks. Okay. Now that was the starting point for deep neural networks. And deep neural networks essentially, if you think about some kind of some thousands and thousands of combination of logistic regression functions. Okay, people later on modified this one, but that was the original case. Okay, so try to understand the fundamentals. Okay, and then we will kind of try to look into the neural network and try to connect the connection between this one and neural network later on. Okay, so again, this is a parametric model. That means it is a functional form with a bunch of parameters, and you have to figure out those parameter values from the data. That's why it is called parametric model. Okay. So what is the mathematical form? You probably know it. The mathematical form is this, that e to the power x by 1 plus e to the power x. That's the mathematical form of this function. Okay. So where x is the input. Now let's try to look into the properties of this logistic regression curve. What are the properties? Now, sometimes it is always like sometimes it's very beneficial to try to understand the properties of these functions in machine learning, what they do for particular kind of data. Okay. So let's try to understand the properties. So what is the maximum value of LRX for any value of x, any real value of x?
1.
Okay. So it's actually close to 1, not 1, because it's asymptotically 1 when you increase this value. What is the minimum value of LRX?
Close to -1.
Minimum value of LRX is what? -1?
No, sir, 0.
Yeah, it's close to 0 actually, yes. Right. Now, when does it attain maximum value?
As x tends to infinity.
At x higher values.
For very large positive number, right? Yeah, okay. So when basically plus infinity or something. And when does it attain minimum value?
-infinity.
Yeah, which is very large negative number. Okay. So that is something the basic properties of this function. Okay. So that is how basically we get to know these things. Okay. Now, this is the shape of the logistic function, right? This is the shape of this function. It basically goes from 0 to 1, from -infinity to +infinity, and this is increasing function. Okay, but as you increase the number, it becomes very smooth. Okay, changes are very small as you increase the number. Okay, right. So people also call it sigmoid function, ace curve, and things, all other things. Okay, just the different names of the same thing. Okay, now let's look at the preliminaries of this model. So preliminaries is basically that it's inherently two-class classifier. Of course, you can extend this to multi-class classification problem, no problem, because many classification algorithms are two-class, but then you can extend to multi-class. But this is inherently a two-class classifier. That means classes are traditionally called 0 or 1. And you can basically convert any two-class classification into 0 or 1. Or you can say positive or negative. Okay? And logistic regression is a probabilistic classifier in the sense that when you have an input feature vector x, it tries to compute the probability that x belongs to class 1. Okay, that's important. So what is the probability that the sample will belong to class 1 given its feature vector? So probability of y is equals to 1, y is the output level given the feature vector x. That is what we are interested in logistic regression. Okay. All right. So next, preliminaries. So small concept that we use called odds. So what is odds? The probability that it will be 1 minus divided by the probability that it will be not 1, rather 0, because it's a two-class classification. So it will be 0. That ratio. Okay, that's called odds. By definition, this is called odds. Okay. Now, what are the properties of odds? This is always positive, right? Always positive. Okay, and it lies between 0 and infinity. Okay, now, do you have any objection on that? Anybody? Okay, all right. So we are going to play with these odds in order to figure out the functional form of logistic regression. So the main assumption, again, this is assumption. Machine learning, you all the time you do assumption. That's the assumption. The assumption is that the logarithm of odds, the odds that we have seen in the previous slide, is a linear function of the features of input x. That's the linguistic assumption. Okay, in terms of language. So mathematically, if I can convert this line into mathematical form, what will happen? So assume that you have n features for sample x. There are n features in the data, and for a sample. So this is something like this. The log of the odds we have said before, is equals to the linear combination of the feature values. So theta 0 plus theta 1x plus theta 2x and so on and so forth. And which basically use z as a shorthand for that. Okay. So that's the assumption behind this model. We assume that. linearity assumption. All right. Now, if you organize this a little bit, you are going to get something like this. The probability of P is equals to will be 1 given that feature vector is equals to e to the power z by 1 plus e to the power z. So same mathematical form that we have seen a couple of slides ago. Okay, the logistic form. Okay. For convenience, we write this one, just a notational convenience. Here the theta refers to the model parameters because you have a bunch of parameters in the model because Z actually consisting of n plus 1 parameters. So I simply use capital the theta to shorthand to represent all this theta. Just a notational convenience and nothing else. Okay. So this is the model structure that we're going to play with. And you know what is Z given the feature vectors. Okay. All right. So what kind of boundary it can model? Can it model all kinds of boundary? No, it cannot model all kinds of boundary. Why? Because you look at the structure of Z. Okay, the Z is basically the linear combination of the feature values. It's a basically linear function, Z. Okay, so it can actually model the linear decision boundary. Okay, so the decision boundary you are basically seeing on blue. So on one side you have one class, in another side you have another class. Because it's the nature of the Z, you can do that. Okay, you cannot go beyond that. Okay, so let's take specific examples and try to understand why I am saying this. So say Z is greater than 0. Okay, when that can happen? It can happen when the point is on the right side of the straight line. Okay, so something like this on this side of the straight line. So then basically Z becomes higher than 0. Now if that is the case, then the probability that that sample will belong to class 1 will be higher than 0.5. Okay. Similarly, what will happen, and this question for you, what will happen, what is the value of probability of 1 for this particular point, the point where my mouse pointer is? This point.
Less than 0.5.
So
less than 0.5. Okay, very good. Now, if I compare the probability values of this and this, which one will be higher? This point and this point.
The one more near to boundary line.
First one.
One more near to the boundary line. Okay, all right. Only because this is closer to the boundary line. Okay, and we are actually interested in the positive class, that's why. Okay, now if I change my definition slightly, for example, just a little bit of like quiz. So if my definition is that probability of y equals to 0 given x, that's the way I formulate my problem, then which value will be higher, this or this?
One far away from the boundary.
Yeah, exactly. Yeah. So that's basically the basic intuition behind this, and that's why we basically do. Okay. So that's the way basically we compute the numbers. Oh, here I'm showing this one. Here the z is less than 0, so naturally you are going to get probability value less than 0.5. Okay. So that is basically the interpretation, the physical interpretation of the logistic regression model. All right. Now, what about the non-linear boundaries? I have seen the linear boundaries here. What about the non-linear boundaries? So only part here is that, now look at this here. The Z, so this is my mathematical form, okay, and the Z is determining the kind of decision boundary that I am taking. Okay, this is the main component here which is telling that what kind of decision boundary I can take. And then this value can give which side of this line you are in. Okay. So therefore, why cannot we simply model the non-linear decision boundary? Okay, and in order to do that, all you need to do, we need to play with Z. Okay, here. So you have, for example, something like this. Okay. Now all we basically need to do, we need to basically use Z appropriately so that we can actually model this kind of decision boundary. That's what basically you have to do. Okay. So if I do that, then basically again from my equation, how far I am from the line will tell me the probability values. The probability values basically will tell me that okay, how far I am from the line, from this curve, okay, and so on and so forth. So if you look at this particular example here, one possible way to do these things in this, from this curve, it seems that this is a quadratic curve. So instead of taking the linear function, which is equals to z in the previous case, we can simply take a quadratic equation here, theta 0 plus theta 1x plus theta 2x square. Okay. So if I change my z here, then I can basically also model this kind of decision boundary. Okay. Again, the same trick we're going to play, how far it is from the decision boundary, and depending upon that, I can say that this is positive or negative. Okay. So the bottom line is that you can actually model any kind of decision boundary using this particular expression, provided that you set your z right. Okay, depending upon this. If a highly non-smooth decision boundary, then you have to increase the degree of the polynomial of z, and then basically you can use it straight away in this model. Okay.
Excuse me, sir.
Yeah, please.
Sir, in this example, isn't it theta 1 x1 plus theta 2 x2 square?
Theta,
like,
sorry, say again, theta?
Isn't that theta naught plus theta 1 x1 plus theta 2
okay,
x2
okay.
square?
Actually, this should be actually y, not actually x. So basically, you know, there are this is univariate function. So there is x, and there is y.
Okay.
Just a mistake here. Thanks for pointing that here. Okay, so yeah, I will stop here because I do not have enough time to proceed further. So in the next lecture, we will talk about how you can estimate this model parameters and all kinds of optimization things that you do in machine learning. So if you have any question, I'm happy to take a couple of questions.
Hello, sir.
Yes, please.
So will you also explain how to implement this in code? All these algorithms.
Yeah. In the lab sessions, we will have that. Of course.
Okay. Okay.
So lab sessions, you will get to know how to implement all these algorithms that you're talking about. Yeah, you get to know.
Sir, why do we need this when we already have polynomial regression?
Sorry?
We already, so you taught polynomial regression today. Like, why do we need?
Okay, why you need this one? So as I mentioned, this is a probabilistic classifier. So where you need to know that the probability values. Okay, that's what. So in regression, you do regression, continuous valued attribute. This is a classification problem. Okay.
So in this, we just add one extra step of calculating e power z by 1 plus e power z over the normal regression, like polynomial regression.
Can you repeat your question?
So like in this, we are just adding one extra step of calculating e power z by 1 plus e power z over the normal polynomial regression.
Right. You are basically converting the whole thing into probability. Yeah, right. Probabilistic classifier. Yeah. Because there are issues. Why? I mean, you get to know why I'm doing this one later. So once you play with the probability values, then you can use maximum likelihood estimators to ultimately you have to estimate the models. Okay, model parameters, and then basically you can apply. You can play with the objective function much more conveniently, and consequently you can relatively easily find out the model parameters using optimization techniques. So it's just for convenience, like that's the physics.
Sir, why can't we do it like the same way as linear regression? Because we may scale the features and then, like in the previous slide, you showed that if greater than 0, if z is if the probability is greater than 0.5, then that is belonging to one class, and if it is less than, then it is belonging to another class. So like if we can also not apply the logistic function and just calculate z, and according to the values of z we can classify. Is it not possible?
Yeah, this is possible, but then so the issue that I mentioned is that you have to get the model parameters, and there you need to like apply some kind of optimization techniques. So you apply construction of objective function and optimize it. So in the thing that you suggested, the objective function would be not continuous in nature. Like you have to basically take a hard cutoff. Okay, say alpha is the cutoff. Say less than alpha in one class, higher than alpha is another class. Right? That's what I think you are suggesting. Right?
Yes, sir.
Yeah, okay. So then the objective function will be of non-continuous nature and difficult to optimize this objective function. But here the function is continuous in nature. You have no such a cutoff. Okay, just the function you can apply, smooth function. And it's a continuous function, and therefore the objective function is easy to handle using optimization techniques. That's the main reason.
Okay, sir. Got it.
How is this method logistic classification advantageous over the previous classification that we learned?
Repeat your question, please.
So how is this classification better than the previous classification that we learned?
Oh, previous classification in the K-nearest neighbor?
Yes, sir.
Okay, so in K, the advantage is this, that here you have, so in K-nearest neighbor, every time when this sample comes in, you have to compute the K-nearest neighbor and then you do it, right? So there is no parameter, that's advantageous, but this computationally complex.
Dada, Arao.
But here in this case, once you learn the model, that means you know these parameter values theta 0 to up to theta n. Okay, for any test sample, it is just manipulating this expression. Okay, you do not need to compute all these complicated things like K-nearest neighbor and this and that. So this is very fast. Okay, to predict.
Okay.
So I just sign off by saying this one. There are online algorithms and offline algorithms. So this is called offline algorithm because once you train this model, you can just freeze this trained model and then you apply. But K-nearest neighbor is an online algorithm. There is nothing learned, you have learned. Okay, whenever the test sample comes in, you simply find out K-nearest neighbor and then do it. So every time you basically new sample coming in, you have to do that same thing from scratch. Okay. Okay, so all right. Thank you all for joining an interaction. And then see you again on Monday. Okay. Okay. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.